My name is Badru Senoga, and I'm here to present a reviewed paper that was about an explainable artificial intelligence module for clustering numerical databases. And these are the authors. I take credit for them. So, as we start this, the main points or the key terms that you need to know before you even start reading the paper, you need to know what is an explainable module. An explainable module is one which can be, you want to find out a model whereby it can, whatever results it gives you or the algorithm it has, is it understandable by the human being? Can it be able to, can you get to know the reasons behind the decisions it has made? So it has to be easy to understand. Then another term that you need to know is clustering. And of course, this is about it's a task of dividing data points into a number of groups, whereby there is more similarity in that particular group, and it is different from the rest of the other groups. So you need to find a way whereby you group them, and they have to be similar. Those data points that are in that same group, they have to be similar. Then about unsupervised decision tree. Unsupervised decision trees. This is about a combination of unsupervised cluster algorithm, whereby it creates the first guess with a first guess of what's good, what is not good, and then on that you can be able to come up with the decision tree can go ahead and split the data accordingly after knowing. The numerical databases, it's about you having a large collection of data. It can be measurement data or observational data that you can have. So we need to know that, and from there, the decision tree induction, what we have here is that we have to find ways, as we talked about the option of you creating the first guess, and then after that you're able to know what is good and what is not. That is what we call unsupervised decision tree. Now here we are just showing the induction process of it, whereby you can go ahead and see you break down, there's the top down and then the bottom up approach for this decision tree induction. But for now, in the slides, I showed that more details about the top down, whereby you start building the root node, which contains all the objects of the training database. So from there, you are able to split the nodes into partitions, or sometimes you can call them children nodes, and then repeat the procedure recursively. You repeat the procedure recursively over the nodes, the children nodes, until some stopping criteria is made. So criteria is more like a standard, or how you can achieve something, or a way that if this is met, you can now do this. So it's more about you telling having a certain scenario met or a standard met. So from the list of these features, and of course after also doing the splitting according to the criteria, the induction process can generate several split candidates, and then at the end of it all, a pruning method can be executed for obtaining the new decision tree, and thus improving the performance. So ideally, you see that we have a set of objects whereby they are compact and isolated, while not similar, they are not. So this is the difference between having unsupervised decision trees. They are compact and isolated, while more similar they are. So you see we have a white line, we have a red line with dots, then the blue one. So you can give let's say a group of people, you say how can you classify this data, or you or put it, how can you divide and put it in a group which have similar traits or characteristics. So someone can come with the red dots and put it in the middle, the vertical one, and and him, of course, human beings have different options. So for you may cluster and put at the left, you group that circle, the small circle and the small triangle at the left, and for you put it as a group. Why? Because it is small. They are all small. They have a common trait. Then the ones at this side, yes, it is a circle and a triangle, but they are big. So that big, the option of size, it is a common trait. Yet another one, when you give them the same diagram, for them they can use the red dots, the horizontal one, whereby he takes it because he decides the top one, yes, the other one is small and this one is big, but they are both circles. So that is also a common trait. Then the one that is below, yes, this one is small, this one is big, but they are all triangles. And in a way, so there are different opinions that can come from different people. So you need to be, as long as the human being is able to understand. So what are some of the works that have been worked on? Some of the previous works done. There is one that was proposed by Rodriguez, and it is about, he called it PCN, and he introduced a term UD3, an algorithm for inducing a binary unsupervised decision tree recursively by computing the feature split, which maximizes the separation of the means of the nodes. So an advantage of this is that you can build trees efficiently. However, this option, the PCN, has 3 drawbacks, and one of that is the fact that the UD3 evaluates a feature split as a separation of the means. The way you see the example 1, example 2, and example 3. So it evaluates the feature split as a separation of the means, considering only separation of the means may cause very different points distribution to the, it may cause evaluating the feature split as a separation of the means, it can cause, considering only the separation of the means, may cause very different points distribution to produce the same mean as illustrated in the diagram. So at first you have a 1 and a 3, then the mean is the one that is in the middle here, where you get the, like, so in our example, the first example, it is okay. Now what about example 2? Realize that someone can have the first data point can be here on 1, then on 2, then another data point can be around 6. Then for it to look for the mean, but now in the under mean there is no data point. So realize that it may not be accurate here. The same applies for example 3. We have a data point at 1, we have a data point at 2, then at 6, but in the middle, in the mean, there is no data point. So it may not be accurate when it comes to us detecting the distribution. Another setback is that UD3 requires parameters that control the number of objects in the leaf nodes, and the authors do not provide any automatic algorithm to compute these parameters. Then another one is that there are some databases where PCN cannot compute the clusters. So they proposed algorithm UD3.5. Okay, so for it takes in account the compactness and separation of the clusters in the left and the right child nodes without sacrificing the efficiency of UD3, because UD3 is efficient, that is good, but then they have that those 3 drawbacks as we've seen, and this is the function that you can use for evaluating criteria for this particular algorithm of UD 3.5. So it has the function which is true1, and then is a sort of sorted set of values for one-dimensional feature. Then k is the index of the value in that particular function, which tags the beginning of the right cluster in one-dimensional feature. So the different, as you see the different items, we also have the LM and RM and the mean values of the clusters in the left and the right nodes. So you can go ahead and evaluate the compactness and the separability of the clusters in the left child node, and then you can also do the same for the right. So this is one of the difference between the UD 3.5 and the UD3. For it considers that compactness and then the separability of these data sets. So as you see in the diagram, there are 4 well-defined clusters of 2D points, and you can see that the first diagram, or the first graph, it represents the feature splits and clusters found in UD3. Then at the side there is one for UD 3.5. But for UD 3.5, you see that it is very well defined, and you can clearly tell that, okay, now this is split 1, this is split 2, this is split 3. You can easily tell, which is not the case with UD3. So experimental framework. For the experiment, they used 40 well-known databases taken from UCI machine learning repositories, and this included the different databases with the different number of objects, different number of features, and number of classes. So from there, to execute the clustering algorithm based on decision tree, so that the clustering algorithm here for unsupervised, we have the PCN, UD3, CoWeb, CLUS, then UREREF, and those not based on the decision tree. These other ones, they are also good, but for them they are not based on the decision, on unsupervised decision tree. That the likes of K-means, EM, DBS, scan. So those ones, we also tested them. We did the execution with that particular model. That is what they were proposing, that they did the execution with that particular model. And of course, they were leveraging with that library, the scikit-learn library. It helps you. It was one that was used, and of course, there are different other protocols that, depending on the clustering algorithm that you're going to execute. But for this particular one, we use the experimental protocol, which is F-measure, to evaluate the cluster results. And of course, this F-measure evaluates the dependencies between C classes in the database and K clusters built by the clustering algorithm. And this is how it is represented in the equation, whereby you have F, the F-measure, and of course it has T, which represents the number of objects in the database. C is the set of classes, K the set of clusters, and precision, number of objects of that particular class. So from the results, we were able to determine the statistical significance of the difference among the clustering results they applied using the Friedman test, and they compared the different results considering the level of significance, which is 0.05. So from this table, as you see the databases and the different algorithms that were used, clustering algorithms, you see that DBScan performed well. You see it has 10 victories compared to the rest. And remember, for us, what they were proposing is the first one, EUD 3.5. For it has 7. However, the number of victories does not determine the clustering algorithm is better than the other one. No. So because you need to know that, knowing this, the group of statistical methods and measures must be applied, like the table below. So we apply more statistical measures or methods, such that, and when we put that on, you realize that the proposed UD 3.5 reached the best ranking, maintaining the second best average compared to K-means. K-means was the first. But of course, you see they are close to each other under average F measure. So one advantage of UD 3.5 with respect to the other algorithm is that it can describe the computed clusters by means of the patterns extracted from every decision tree. These patterns are short and easy to understand by the expert in the application area, because it has to be an explainable AI that can be understood by the human being. So in conclusion, these algorithms based on unsupervised decision trees provide an easy way for describing each cluster by following the path from the root to the leaves. And in this particular paper, these authors proposed the UD 3.5 as a new algorithm for inducing a collection of diverse unsupervised decision trees, and it relies on the new split evaluation criteria, which improves the performance of PCN, which was already working fine, but this time they added in something extra because they didn't want to leave out that part, the good part of PCN, which was satisfying efficiency. So their proposal reached the best position in Friedman's ranking compared with other popular state-of-art algorithms. And so this can be used, unlike the other algorithms based on the decision tree, their proposal does not require any parameter that controls the number of objects in the leaf nodes, the way we saw it at first. And also it is automatically it stops the expanding of branches. If a new child node evaluated worse than the best evaluation computed in the branch, because those ones that we don't need, they can be removed from the data set, the data points. So we remove out the dirty data points that we don't need, that cannot improve the performance of the model. We want only those ones that can give us the best results and performance. So the important advantage of this proposal is to provide patterns associated with each cluster, describing the whole database with a few patterns by keeping those which are more general. And of course, this is more easily understood and can be applied in other applications such as biotechnology, psychology, banking sector, medicine, where specialists analyze the clusters for accepting or rejecting any hypothesis or a theory that you see you have data but you don't understand. You want to easily design and a study, you get to be able to understand and explain the phenomenon or situation according to the data that you have. And those are the references. Thank you very much.